Well, I hope things are going well for you today. We're going to go ahead and get started into our third chapter of geography. So let's get organized. For your materials today, you want to have on hand Activity 3.1. That's going to be for part of your assignment, so you won't need it actually during the lesson. On the agenda for today, we are talking about heat in motion, and we're going to be using the globe for some demonstrations to help you understand the concepts we're talking about. For our main idea today, the seasons result from the way sunlight hits the earth. Pretty simple idea, often misunderstood though. The goals for today: explain the basic cause of seasonal changes, identify the imaginary boundaries between latitude zones, identify the 3 latitude zones and distinguish their basic characteristics. Okay, so 3 things ahead of us that we want to accomplish today. Let's go ahead and start our lesson with our chapter verse. Go ahead and read this with me, Genesis 8:22. While the earth remaineth, seedtime and harvest, and cold and heat, and summer and winter, and day and night shall not cease. Now, last chapter we looked at the days of creation and learned that God created the water and land with a special balance, and that any change in the relative proportion of land and water would have drastic consequences for life on earth. And God had great wisdom in designing not only the water molecule, but also the proportion on the whole face of the earth. And today we're going to look at another of God's carefully balanced designs, the Earth's atmosphere. And it's one of the most arresting facts of the Earth when seen from space. You can see that it's constantly shifting, and it's what provides for man's basic needs, the air we breathe, and much more, which we'll be learning about. And the complex variety of weather patterns also supports a great variety of life. So we can learn even just from that statement right there that God is a God who loves variety. He didn't create us all the same. We don't look the same. We don't talk the same, act the same, or think the same. He created us differently, and He created a great deal of variety in His earth. Okay, our first topic on the agenda today is heat in motion. So we want to find out, how does heat move around the earth? How is heat distributed? Basically, by the seasons, by the winds, and by the ocean currents. And today we're going to focus on seasons, and we'll get to winds and ocean currents in future lessons. So as we learned from our chapter verse, God has promised that as long as the earth exists, there will be seasons, won't there? And seasons are the most obvious evidence of the sun's influence. You're probably most familiar with 4 seasons, right? Temperate. If you live in a temperate zone, you're familiar with spring, summer, fall, sometimes referred to as autumn, and winter. But other areas of the world are actually limited to just 2 seasons. Do you know what they are? There are 2 areas outside the temperate zones where the seasons are limited to just 2. One area is the tropical area, or the tropics, and their seasons are rainy, and it's pretty simple to figure out the opposite of that, dry. Then the polar regions also have their own seasons. We can refer to them as seasons. One is constant darkness, and the opposite of that would be constant daylight, right? It's also referred to as midnight sun. The sun is out all the time. We'll be learning more about the 3 regions, temperate, tropical, and polar, but first we're going to turn our attention to the reason for the seasons. As we saw in our main idea, the seasons are the result of what? Were you paying attention? Do you remember it? The way the sunlight hits the earth. And there are 2 major factors to consider. Why do we have seasons? The way the sunlight hits the earth. We're talking about the angle of the sunlight and the tilt of the earth on its axis. Now, as the sunlight hits, we have 2 basically two types of rays, I like to call it. We're going to have direct rays coming straight down and diagonal rays. Okay, so we have direct rays. That's how I'm going to refer to them. You could choose other names, but we have direct rays of sunlight and diagonal rays of sunlight. Okay, this diagram, and you can also find this in your textbook on page 38 to get a little better view, shows direct rays of sunlight. They're traveling the most direct path through the atmosphere to the Earth's surface. And the most direct path is obviously going to be the shortest distance. More of the rays will reach the surface and surface of the Earth, and the land is going to receive more sunlight. Okay? So the rays are coming straight down, hitting the Earth, and the Earth receives the most sunlight. Where does this take place? Along the equator, right? You know that, and as we'll learn today, or you might already know, the surrounding areas, not just the one little strip, but the area around the equator. What then happens at the other areas on the Earth's surface? If the direct rays are coming to the equator in that area, what's going to happen to the rest? The rays are going to be slanted, aren't they? This diagram, also from page 38, shows the diagonal rays of sunlight. You can see that they have much further to travel, and the atmosphere absorbs most of the energy before it even reaches the land. So that is the big difference there. The atmosphere is absorbing the energy because the rays have further to travel. What portion of the Earth receives the rays with the greatest slant? If the direct sun is coming in at the equator, the poles are going to receive the greatest slant, aren't they? Okay, so that is our first factor, the angle of the sun's rays hitting the Earth. Okay, so at the poles, the rays are more angled, the energy is being absorbed. At the equator, the rays are direct, and there's more heat there. The second factor that we have to consider in seasonal change is the Earth's tilted axis. And this is very important. This is the major factor. Seasons change as the Earth travels around the sun. You've known that for years. And if you've had Earth science, you probably know a great deal about this already. So let's have a little review and see what you remember about the Earth's orbit. All right, like each of the planets in our solar system, our Earth revolves in an orbit around the sun. Traveling at speeds in excess of 30,000 miles per hour, it takes the Earth only about 365 days to make one complete revolution around the sun. The Earth's orbit is not a circular path, but remember this from science, elliptical one that takes it on a journey of nearly, how many miles? 300 million miles through space each year. On this elliptical path, which is called the Earth's ecliptic, the Earth's distance from the sun ranges from 91.5 or 91 and 5/10 to 94 and 5/10 blank miles. How many miles? Million miles away from the sun. The location of the Earth in its orbit when it is nearest the sun is called the perihelion, and the aphelion is the point farthest from the sun. All right, how did you do on your little science brush up there? Did you remember some of it? I didn't give you a lot of time, and maybe you haven't been studying too much over summer break. We're just getting into the year. But those are some things that you've probably already studied before, and they're just a little bit of review. However, We ended up talking about the Earth's nearest and farthest distance from the sun. It's important to remember that it is not the change of distance from the sun that brings the changes of summer and winter. That's why I said our main concept is often misunderstood. People are like, oh yeah, I know about the seasons, and they think it has to do with the path. And when it's really far away, that's when it's winter and so on. But it's not the distance from the sun. Actually, the effect of the direct sunlight is more powerful than the effect of the increased distance from the sun. Okay? So we want to make sure that we don't think that it's the distance. It's not the distance. You can see on this diagram, this is also from page 38 of your text, you can see that in the winter and the summer, the Earth is farther from the sun than it is in the fall and the spring. But look, in the winter and the summer, it's pretty much the same distance. It's not exactly, but you can see that we're very far from the sun in the summer as well. So it's not, again, it's not the distance. Okay? The Earth is actually at its aphelion during the northern hemisphere summer. So it's at its farthest point from the sun during the summer. Also, you want to notice that this illustration shows a dark side and a light side of the Earth. You can see that, and that's because the sun can obviously only strike half of the Earth at a time. And just for a point of reference, the lighted area is called the circle of illumination. You can see it kind of moves, kind of changes where it is depending on where the Earth is in the drawing. That's the circle of illumination. All right, so you want to remember it's the slant of the sun's rays, not the distance from the sun, that affects the seasons. However, it's the tilt of the Earth on its axis that allows the direct rays of the sun to fall in different areas throughout the year. Okay, if the Earth wasn't slanted, the sun's direct rays would hit in the same spot all the time. So I'm going to try to use the globe to explain this a little further. This is my little, this is great. The cheapest things are always the best, I think. This is just a piece of paper cut to kind of fit our Earth here. We can put, the sun isn't anywhere, we can put the sun anywhere we want to. But you can clearly see from this piece of paper, I'm just going to use it here for sample, for sake of illustration, the direct rays travel a shorter distance. The slanted rays have to travel further to reach the Earth's surface, okay? Now, of course, our sun would be hitting, the direct rays would be hitting more near the equator, and then these rays are slanted, and even to get to the poles, they'd be slanted even further. Now, what I want to show you is that if there was no tilt, say that we stand the Earth up straight, this is our sun, and it's kind of hard to make the Earth look like it's going around the sun here, so just for the sake of illustration, I'm going to make the sun move, but we know that it's actually the Earth that moves around the sun. If the Earth was just straight, and it moved around the sun, the direct rays of the sun would hit at the equator all the time, wouldn't they? They would always hit right at the equator. However, the Earth is tilted, and that allows the direct rays to hit below the equator, at the equator, and moving on even above the equator. So this is what's making our difference in the seasons. I'm trying to move as straight as I can. Below the equator, at the equator, and above the equator as the Earth revolves around the sun. Now the tilt of the Earth on its axis remains constant at 23.5 degrees. You probably learned that in science, and the axis consistently points toward the North Star. I don't know if I have it pointed toward the North Star now, but in reality it points toward the North Star. However, as the Earth revolves around the sun, the direction of the tilt appears to change. Let's look back to our seasons diagram, and you can see how in the winter, look at winter, the North Pole is actually pointed away from the sun. See that? And the North Pole is actually in the shadow at that time. That's during the time that the North Pole has constant darkness. However, at the same time, look at the South Pole in the winter. The South Pole is pointed toward the sun, and it's receiving constant sun. Now, see how the poles are opposite in the summer? Look over at summer now. The North Pole appears to have changed. It's still pointing toward the North Star, but it's also now pointing toward the sun. Okay, it hasn't actually changed tilt, but it's now pointing toward the sun, and it is receiving full sun. You can see the South Pole is pointing away from the sun, and it is in constant darkness. Okay, so if the Earth wasn't tilted, they would both receive the same amount of sun all the time. And that's what I was just showing you with our little paper here. If the Earth wasn't tilted, all of the areas of the Earth would receive the same amount of sun all the time. But it is tilted, and therefore we have our seasons. So we're going to look at a close-up of the Earth and how the sun's rays actually hit it on December 21st during the winter. Here you see the North Pole is slanted away from the sun at this time of year. The tilt of the Earth's axis allows the sun's direct rays to hit the Earth at 23.5 degrees south of the equator. 23.5 degrees, that's the tilt of the Earth, so it's that same amount south of the equator. Those are the direct rays of the sun that oftentimes hit right at the equator. This is the lowest point the sun's direct rays will reach, and this line of latitude is given a special name that you've probably learned before, the Tropic of Capricorn. Now, as the Earth travels around the sun, different parts of the Earth receive direct sunlight. That's what we just saw. I'll show you one more time so that you get the idea. The Earth is traveling around the sun. I have to make the sun move, so it's kind of hard to keep it straight. So the Earth is traveling around the sun. You can see now the farthest north that we're going to get is going to be our Tropic of Cancer as the Earth travels. The farthest south is going to be the Tropic of Capricorn, 23.5 degrees north or 23.5 degrees south. That's what allows us to have the direct rays of the sun hitting in different places of the Earth. Now the tropics, you want to remember, they're important. The Tropic of Cancer, 23.5 degrees to the north. If you can remember the tilt of the Earth's axis, you can remember that easily. That is the northern limit of direct rays. The direct rays are never going to go above that. The Tropic of Capricorn, 23.5 degrees south, the southern limit of the sun's direct rays. Okay, now, as we saw in the illustration, during the northern hemisphere's winter, the North Pole receives no sunlight, while the South Pole receives constant sunlight. So it's tilted this way. The North Pole isn't getting any sunlight. It's on the half of the Earth the sun doesn't shine to. The South Pole is getting constant. You can see how the South Pole then is going to be tilted toward the sun. It's getting constant sunlight. Now, the latitude lines marking those areas that have the two seasons, the complete darkness and complete sun, are known as circles, and they mark the polar regions. Okay, the Arctic Circle, 66.5 degrees north. That is the limit of complete darkness or sun in the northern hemisphere. The Antarctic Circle marks the southern hemisphere's polar region, 66.5 degrees south, and the limit of complete darkness or sun in the southern hemisphere. All right. Now these special lines of latitude that have been named also distinguish our three basic zones that we talked about. This is one of your things you were supposed to get today. The latitude zones. We've already referred to them, the tropics, the temperate zones, and the polar regions. The tropics, the temperate zones, and the polar regions. And if you will, go ahead and turn in your textbook to page 39. And we'll see a diagram of these showing us. Now here they have the Earth straight. We know it's actually tilted, but we can look at it this way. We can see it a little bit better. We have our north and our south poles marked, 90 degrees north and south latitude. Our polar regions are at the poles. That's pretty easy to remember. That's what we just looked at, 66.5 degrees north and south. During part of the year, the North Pole will have complete darkness while the South has complete constant daylight or midnight sun, and then it will be reversed. The other will have complete darkness and the other complete sun. Those are the two seasons. Then we have our temperate zone. Our temperate zone is the area of the Earth that's going to have 4 seasons: spring, summer, fall, and winter, the temperate zones, and those are between the polar regions and the tropics, 23.5 to 66.5, both in the northern hemisphere and the southern hemisphere. Then we also have our tropics. Those are along the equator. That's why I said you'll see the direct rays of the sun shine on the equator and the surrounding area. These are the areas that receive the direct rays of the sun. Remember, the direct rays of the sun are never going to go above 23.5 degrees north or below 23.5 degrees south. So this marks the area of the earth that can receive the sun's direct rays. All right, notice that we also have some other terms next to these here. High, middle, and low latitudes. Now you might wonder how they got their names, because it looks like, I would think of this as being maybe high, because, oh, it's hot there or something. But the low latitudes, or maybe think of the bottom as being low, and this would be high. The low latitudes are named because of their numbers. The equator is 0, right, up to 23.5, so that's low numbers. We have the middle latitudes. Those are the middle numbers, 23.5 to 66.5. The middle numbers. And we have our high numbers, 66.5 up to 90, and those are the high. That's as high as our latitude goes, 90 degrees. So it's taken from the latitude numbers, the lines that are the boundaries between the regions. All right. Now, some places also have a little bit different numbers, like they'll say 30 to 60 degrees instead of being really specific and saying 23 and 5/10 and 66 and 5/10. The special lines of latitude also help us mark the beginning of each of the 4 seasons. And this is probably also a review for you, so let's see what you remember. All right, now I have our seasons written out. Summer, autumn, and I have a little suffix there, winter, and vernal. That would be spring. All right, so our seasons are named a little bit differently when used with the terms solstice and equinox. Those probably ring a bell to you. Do you know what summer is? Is summer a solstice or an equinox? Summer is a solstice. And do you know the date that summer starts? This is probably one you've known. Oh, you're always counting down to summer. Summer starts June 21st. And June 21st is the referred to as the summer solstice. It is the first day of summer. But why do we use the term solstice? It's the day when the direct rays of the sun shine along the Tropic of Cancer north of the equator. So the direct rays of the sun are on the Tropic of Cancer. See if I can find it quickly here. It should be 23.5. So right in here, the direct rays of sun are shining here. So that's when our summer starts. That's as close as the sun's rays are going to get to us. And as the Earth continues its orbit after the summer solstice, the direct rays of the sun move slowly. What happens after summer? It gets cooler, right? So the direct rays of the sun move slowly southward until they reach the equator on what day? This is going to be our equinox. Think of equator, equinox. Autumn starts on September 21st, my mother's birthday. And when we use our suffix, it's the autumnal equinox. All right? Then we have the winter. What do you think? Solstice, isn't it? They're changing. The solstice, where do you think the sun's rays are going to hit? Right over the Tropic of Capricorn, right? So we have solstice, equinox along the equator, solstice. And the winter solstice, the sun is directly over the Tropic of Capricorn in the southern hemisphere. That's as far as it's going to get from us. That's why it's winter time for us. The direct rays of the sun are hit the Tropic of Capricorn on, do you know what day? December the 21st. Are you noticing a pattern here? All right. Then the rays of the sun move back up to the equator for what season? It's going to be vernal, so that's spring for us. Is it going to be a solstice or an equinox? The equinox, right? Think of equator, equinox. And when does spring start? You should be able to figure it even if you can't remember. March the 21st. You can see, take your 12 months, divide by 4, so every 3 months, then the seasons are changing. Now the solstices, remember, mark the 2 days of the year when the direct rays of the sun shine the greatest distance from the equator. So all the way up to the Tropic of Cancer and all the way down to the Tropic of Capricorn. Those are the times when the 24 hours of perpetual sunlight is occurring at one of the polar regions, and 24 hours of perpetual darkness is occurring at the other region. Okay, the solstices. Now the equinoxes, again, are the 2 days of the year on which the direct rays of the sun hit on the equator, giving all of the earth an equal amount of daytime and nighttime. All right, so remember, the earth's constantly moving, so there's this one 24-hour period when the rays are right on the equator, and then it moves on. And the rest of the time they're moving up to the Tropic of Cancer, back down to the equator, back down to the Tropic of Capricorn, and so on. So we've pinpointed the days where the sun shines in those different areas. All right. Now, that is going to wrap up our lesson today, but since it's our first lesson of the chapter, let me go ahead and tell you about your current events assignment. All right, you want to look for a recent article that has climate as its topic. I know that's pretty general, so let me give you some topics, anything to do with the seasons, anything that we talked about today, solstices, equinoxes, tilt of the axis, things like that. Anything to do with winds we'll be talking about next time, ocean currents in the next lesson, weather, and so on. So you might want to even just want to flip through the chapter, get an idea what type of article you're actually looking for. And of course you'll want to put that article in a notebook, note the title, source, and date. And the most important thing is to write yourself a brief summary of the article so you know that you've read it and that you understand it and you can repeat it in your own words. That way you make that information yours and you can share it with others and share it with your family. Okay, now let's go ahead and take a look at your assignment. Okay, you want to go ahead and read pages 37 through 39. That will fill in all the gaps that I left during the lesson. And then your section review on page 39, you'll want to answer those questions based on your reading. Also, activity 3.1, number 6. We're going to look just real quickly at this activity together. This is one of those, again, that you'll be working on kind of throughout the chapter. I think we did one like this last chapter as well. It's a climate of the world map. The map is actually on the next page, and then these are questions. This tells you what to do on the map. Some of these are questions. Number 6 applies to our lesson today. Look at the map of latitude zones on page 39, which is what we just looked at together, and then you can use that to label the tropics, the temperate zones, and the polar regions, okay? And that's going to go on the map on the back. I've already got some answers on mine, so I won't flip it over and show it to you. But these other ones, I've kind of marked what section they go along with, and I'll just assign 1 or 2 to go along with each lesson, and so it won't seem like a big task because some of the other lessons have their own activities to go with them, and you're not trying to do 2 or 3 activities per lesson. Okay, now let's give you something to think about as you're reading. How did God create variety in seasons for those of us on earth? How did he do that? And also, where in the world was writing invented? See if you can find the answer before we meet back next time.